Welcome to section 4.3, part 2. Here we will be exploring the second derivative and the many things that it can tell us. Two of those things are points of inflection and concavity. Before we get into those specifics, we want to first focus on the second derivative. So before getting there, let's just talk about what the first derivative tells us about a function. The first derivative tells us about a differentiable function. It tells us the rate of change of that function, or how our first function is changing. We've already discussed in depth the relationship between a function and its first derivative, mainly that if the first derivative is positive, that means our function's increasing. And if our first derivative's negative, that means our function's decreasing. Therefore, f double prime, or the second derivative of f of x, tells us how the first derivative is changing, or the rate of change of f prime of x. In an extremely similar way, if our second derivative is positive, that means that our first derivative, f prime, is increasing. Then, if our second derivative, f double prime, is negative, can you guess what that one means? It means that our first derivative is decreasing. This is not as easy to see visually on a graph as it is to see literally f of x increasing or decreasing, because normally we have graphs of just the original function f of x. So while it seems simple here, this is a lot more theoretical because we normally don't see this as clearly. But in the next slide, we're going to take a look at what it really means for f prime to increase and decrease, and what our second derivative really looks like, and that is concavity. Concavity is defined as either being concave up or concave down, and concavity is kind of what a graph looks like. I like to think about it if the graph will hold water or spill water. So if we look at this, so this is the graph of some function f of x, and it's split up into like 3 sections from left to right. And we can see in this first section here, this part of the graph would hold water. If water was like poured onto it, it would like, come and just be held here in the graph. And the graph is concave up. It's like a smiley face here. Then in this middle section here, the graph would not hold water. It would spill water. So if it rained here, then it wouldn't hold here. It would like fall off of the graph. And the graph here is concave down, and it's like a frowny face here. Then at this point here, our concavity changes once more, and again we're concave up. So f double prime, or our second derivative, is positive, greater than 0, at both of the intervals where our graph is concave up, and the second derivative, f double prime, is negative, or less than 0, where our graph is concave down. So concavity is directly in line with whether or not the second derivative is positive or negative. A positive second derivative is concave up, a negative second derivative is concave down. We saw previously that the second derivative shows how the first derivative is changing. And so if our second derivative is positive, like here and here, then that means that our first derivative is increasing. Let's explore what that means by using the tangent lines, which are our first derivative. So if we were to draw some tangent lines here going from left to right, remember that the first derivative is the slope of the tangent line. So we'll draw this tangent line, we'll draw another one here, and we'll draw one here, and then finally we'll draw one over here. So they're not the world's best drawn tangent lines, but that's okay. So I note that I drew 4 tangent lines in this part of our graph that is concave up. We are claiming that f prime is increasing, so that means the slope of all these tangent lines should be increasing. Now, the slope of the tangent line here is a very steep negative number. I do not know exactly what it is, but this tangent line almost looks vertical. So it is very starkly decreasing here. That means the slope of our tangent line here is a negative number with a large magnitude, meaning it's very negative. I'm going to put a number to this that is just made up. So let's say that the slope of this line is negative 10. Then if we look here at this next point, our tangent line is still has a negative slope, but it's less negative. It's not as steeply decreasing as the first one. So let's say that this tangent line has a slope of -8. Again, the slope of the tangent line, recall, is f prime, and we want to claim that f prime is increasing. So it's already increased. From -10 to -8, that is an increase of 2. Then this right here, this tangent line is horizontal, and because we have a relative minimum here, the slope of this tangent line here, our f prime, is 0. And then we can see that the slope of this tangent line is positive. Therefore, the slope of this tangent line is a positive number. So let's say it's +5. It doesn't quite look as steep as like how this one is steep. Either way, again, I'm making these numbers up, but what I'm not making up is how they're related to one another. They are increasing as we look from left to right. So f prime is increasing. It's kind of weird to think about, but f prime is negative, less negative, 0, and then positive. Even negative numbers can increase. So when we're concave up, that means that our first derivative is increasing. Similarly, when we're concave down, that means that our first derivative is decreasing. That means that as we draw the tangent lines from left to right in this section where we're concave down, their slopes will decrease. So I'm drawing 3 tangent lines, and again I'm going to estimate what their slopes are. So it looks like our slope here is slightly less than 5 because our slope is slightly less steep. So let's call that a slope of +3. It's positive. Then we can see that because we have a relative maximum here, our tangent line is horizontal, therefore f prime is 0 here. And then we can see that this tangent line here has a negative slope. It's going down from left to right. Our function is decreasing there. And so let's say that slope is -3. So again, I am making up these, not this one, but I am making up these numbers of 3 and -3, but what I'm not making up is how they're related to one another, meaning our slopes go from positive to 0 to negative. They're decreasing in this section here, the slopes of our tangent line. Therefore, when the second derivative is negative, it means f prime is decreasing. In a similar way, our last interval on our graph here is concave up once again, and the slopes of our tangent lines would be increasing. I won't write them all out here, but they go from negative to 0 to positive. So they are again increasing. We just explored concavity graphically and what it means, and now we want to learn about how do we test for concavity algebraically. Well, as long as f of x is a twice differentiable function, meaning that both f and f prime are differentiable on some interval, then we know that the graph of f is concave up if the second derivative is positive on that interval, and it's concave down if the second derivative is negative on that interval. So in more layman's terms, if f double prime is positive, that means we are concave up, or CC up for short, and if f double prime is negative on that interval, we know that we are concave down. How do we determine those intervals? Let's see. In our first example, we are going to test for concavity. We want to find the intervals on the graph of our function f of x. It's a cubic function, and we want to find the intervals where we're concave up and concave down. Well, when we're dealing with concavity, we want to first find the second derivative, so that's going to be our first step. So let's first find f prime using the power rule. F prime will be 3x squared minus 4x plus 5. And then f double prime, the star of the show, that's how we determine concavity, is going to be 6x minus 4. Now, since we care about where we are positive versus negative, where our second derivative is positive versus negative, we need to figure out where that change occurs between positive and negative second derivative. Whenever you are asked to determine where something's positive or negative, we care about setting it to 0. 0 is the great divide between the positive and negative world. That is why 0 is so important in mathematics. Well, one of the reasons. So we want to set our second derivative equal to 0 and then solve. Yes, this is very similar to other things we've done before, such as the first derivative test and finding critical points with the first derivative. It really is a very similar idea, except it's just with the second derivative. So we're going to solve and simplify, and we'll get that 2/3 equals x. That means that the second derivative is 0 at 2/3. Because it's 0 there, there's a potential that we had a change in concavity there. So the next thing that we're going to do is make a sign chart for f double prime to determine what the sign is. Well, we care about 2/3 because that's 0. And that's where f double prime equals 0. That's what we just set it to. So now what we want to do is, this looks familiar hopefully, is pick a number in this interval to the left of 2/3, pick a number in the interval to the right of 2/3, and test f double prime. If f double prime's positive, it means we're concave up there. If f double prime's negative, it means we're concave down there. So let's test some points right here. So let's plug in a number to the left of 2/3. I'm going to test 0 because that's to the left of 2/3. So if I plug in 0 there, we'll have 6 times 0 minus 4, so that's a negative. Then I want to test a number to the right of 2/3. I'll test 1. When I plug in 1, I'll have 6 times 1 minus 4. That's a positive number. So here's what we know. We know that our second derivative is negative from negative infinity to 2/3, open. And we know that our second derivative is positive from open 2/3 to infinity. I'm saying open because we're not including 2/3 on this interval, since our second derivative is 0 there, not positive or negative. So we can conclude that our graph is concave up when the second derivative is positive, which is from 2/3 to infinity, and our graph is concave down when our second derivative is negative, which is from negative infinity to 2/3. Now, what about that special point of 2/3? That special point of 2/3 would actually be a point of inflection because it's where the concavity changes. So by definition, a point of inflection on our graph is a point where the concavity changes, which is otherwise known as the place where the second derivative changes signs. Let's take a quick peek back at example 1 real quick and determine if we have a point of inflection. A point of inflection, like we just saw, is where our concavity changes, or otherwise known as where our second derivative changes sign. So if we look back at our sign chart, does our second derivative change signs at 2/3? Yes, it goes from negative to positive. Our concavity changed from down to up. Therefore, when x is 2/3, we have a point of inflection. So we do have a point of inflection at x equals 2/3. I don't have my calculator with me, so I did the math really quick on what the y value would be by plugging in 2/3, and I got negative 7/27. I'm going to hope that that's right. I did, of course, plug that back into our original function f of x because we are looking for the y value on our original function. We're looking for the point of inflection, which is on our original function. We do not plug this into the second derivative, a, because it would just give us 0, but b, because we're looking for a point on our graph, not a point on the second derivative. Anyway, because our second derivative changes signs and we change concavity at x equals 2/3, 2/3 comma negative 7/27 is a point of inflection on our graph f of x. In example 2, we want to determine the intervals of concavity, where we're concave up and concave down, and then in part B, find all the points of inflection. So again, we're dealing with concavity and points of inflection. We want to find the second derivative. So let's first find the first derivative, and we need to use the quotient rule here to find the first derivative. So we're going to have low times d high. So we'll have our denominator times the derivative of x, which is just 1, so I'm not going to write it, minus high d low, the derivative of the denominator is 2x, all over low squared. Now I want to simplify this a little bit to make it slightly easier. So this term right here is 2x squared. So we're going to have x squared minus 2x squared. So we'll have minus 1x squared plus 1. I'll actually write that the other way. 1 minus x squared all over x squared plus 1 quantity squared. Now it's up to you if you want to actually multiply this out or just leave it be. Either way is fine. It can work either way to find the next derivative here. So we have f prime. Now we need to find f double prime. So f double prime, again, we will use the quotient rule. So we'll have low times d high. The derivative of the numerator is negative 2x minus high times d low, the derivative of the denominator. The derivative of the denominator using the power and then the chain rule will bring the 2 out front. Then we leave the inside function b, raise it to 1 less, so the first power, then multiply by the derivative of the inside. All over low squared. So something's already squared, and then we're going to square it again, so we're just raising it to the 4th power instead. Then we'll keep going. So simplifying in our numerator will look like, I'm actually not going to do, what I actually see here is this x squared plus 1 in both terms, so I want to just factor that out. And we can actually see that there's a couple things that we can factor out from each one of these here. The first thing that I see is the x squared plus 1, so I'm going to factor that out front. Then there's also a 2 and an x that are in both of these terms. And so I'm going to factor that out as well. And it looks like both terms are negative, so I'm going to factor out a negative 2x as well from both. Let's see what remains in this first term after I factored out a negative 2x and one of the x squared plus 1s. I'm left with just one of the x squared plus 1s. And then in the next term, I am left with a couple things. I'm going to have a plus, and because we factored out the negative, and it looks like we already factored out a 2x and the negative and this x squared plus 1, so we're left with a 2 and this right here, 1 minus x squared. So we're left with a 2 and a 1 minus x squared. All over our denominator, which is x squared plus 1 to the 4th. Now from here, we still have that out front. Look at what can cancel because it's factored out front. An x squared plus 1 can cancel, so we'll be down to 3 of them here. So this one cancels, and this will go down to being cubed. So in our brackets up here, we have an x squared plus 1 plus 2 minus 2x squared from distributing that 2. And in our denominator, we have an x squared plus 1 quantity cubed. Moving ever so ahead, this is a long one here, a long problem. We are left with a 3 minus x squared in here. And I guess we don't really need brackets anymore because we just have that one set of parentheses now. All over x squared plus 1 quantity cubed. Phew! All right, we found the second derivative. Cool. So our next step is to figure out where f double prime is 0 or where it might be undefined. Now, we need to make sure that wherever we find that f of x is differentiable there, if we take a look at f of x, it does not have any points of discontinuity or non-differentiability, so we are okay. Our denominator can never equal 0. If we take a look at f double prime, we want to set both the numerator and denominator to 0. Now, before we do that, I take a look at the denominator. The denominator can never be 0 because x squared plus 1 will always be positive. No matter what we plug into x, we then square it and then add 1. That's always positive. And if we cube a positive number, it's always positive. So our denominator can never be negative. Therefore, f double prime is defined everywhere, but we just need to set the numerator equal to 0 to see where it equals 0. So we have the numerator set equal to 0, so we'll set each factor to 0. We'll divide both sides by -2 to get x equals 0. And then over here, we'll have x squared equals 3 when we add x squared to both sides. When we do this and we take the square root of both sides, we do have to remember that plus or minus in front. So x equals plus root 3 and minus root 3, two x values there. The next step is to make a sign chart to determine concavity. And we want to put those three values on our sign chart in order from least to greatest. So we'll have negative root 3, we'll have 0, and we'll have positive root 3. And that's our x values, and we want to test f double prime. We know that if we plug in any one of these three values, we will get 0 out for f double prime. But we want to plug in other points into f double prime. Now, what we just talked about is that f double prime, yes, it looks complex, but the denominator is always positive. Because the denominator is always positive, we don't necessarily care about it. No matter what, it's not going to affect the sign here because dividing by a positive number does not affect that. So we really are only plugging in to this numerator here. When we do that, let's plug in a number to the left of negative root 3. Let's plug in a number like negative 10 because it's very far negative. So if we plug in negative 10 just to that numerator portion of f double prime, we'll have a positive out front, and then inside our parentheses, we'll have 3 minus 100, and that's negative. So this would end up being a positive times a negative, which is a negative. I'll do one more. F double prime, let's test a number in this interval here. Let's test the number negative 1. So if we test negative 1, we'll have a positive out front. Negative 2 times negative 1 is a positive, and then we'll have 3 times 1, which is a positive. So that is positive. All right, plugging in a couple more points, we end up getting an f double prime sign chart that goes from negative to positive to negative to positive. So we end up having two intervals of our function being concave down, and then we have two intervals where our graph of f of x is concave up. So in part A, our answer is that our graph of f of x is concave up on the interval from negative root 3 to 0, union root 3 to infinity. And then we're concave down on the following intervals here from negative infinity to negative root 3, and then union 0 to root 3. Part B is fairly simple once we have our sign chart for f double prime. To determine the points of inflection, POI, we want to see where the second derivative changes signs, and the second derivative changes sign when x is negative root 3, also where x is 0, and then also where x is root 3. Plugging these values into our original function f of x will give us the following three y values. Wasn't too bad to plug those in. So we have the following 3 points of inflection. So I've zoomed in pretty far on this graph here of our original function f of x, and I plugged in the 3 x coordinates and then got out those y coordinates for point of inflection. This is in fact negative root 3 over 4 and then positive root 3 over 4 is a decimal. I double checked that we did it right. So we can see that this is the first point of inflection. And sometimes points of inflections are hard to see, but we are going from sort of being concave down to this is where we start to become concave up. It's sort of like the point where our graph would stop holding water, basically here. It would start to spill at this point into this section here. So this is our first point of inflection. It's this coordinate point here. We go from concave down to concave up. Then our second point of inflection here is at the origin 0, 0, and this is where we change from concave up to being concave down. Our last coordinate point, we have a couple more on here. I didn't mean to have those on there, but this is the last point of inflection here at root 3, comma, root 3 over 4. And this is again where we go from being concave down to sort of arcing back up again to being concave up. So again, these are hard to see on certain graphs, definitely, especially ones that are so nuanced like this, and you really have to zoom in to see the change. But it is possible to sort of view those inflection points on our graph, which is really cool. Here's our last example. We want to determine, again, the intervals of concavity and then find all the points of inflection. So in order to do anything that has to do with concavity, we need to find f double prime. The first thing we're going to do is find f prime. And we see that we have a product, so we want to use our product rule. We'll have u is x cubed, therefore u prime is 3x squared. V and v prime are both e to the x. E to the x, again, is its own derivative, which is pretty cool. So f prime is going to be x cubed e to the x plus 3x squared e to the x. Now this is a pretty interesting thing because, again, like x cubed e to the x is now part of our first derivative. That was our original function. So when we are deriving the first derivative to get f double prime, we're doing the same thing here. So this first term is going to end up just being this. It's doing the product rule again. So our first two terms in our second derivative will just be what we just got from here. So it's going to be using this again, our product rule u and v. So it's going to once again be x cubed e to the x plus 3x squared e to the x. Then we have to find the derivative of this guy right here using the product rule again. So this u and v, u this time will be 3x squared, and v will be e to the x. U prime will be 6x, and v prime will be e to the x. Pretty cool. So we're going to add on 3x squared times e to the x. I love these patterns. They're so fun. Plus 6x e to the x. All right, so that's our f double prime, these four terms here in two different colors. And so what we want to do is set that equal to 0. Now, setting something equal to 0 is a lot easier if it's factored. So let's take a look at all four terms and see if there's a GCF we can take out. It looks like all four terms have an x and an e to the x in it. So our GCF will be x e to the x. Then we want to see what remains in each term. In this term, what remains is an x squared. In this term, what remains is a 3x. Same with the next term because they're the same. And in the last term, what remains is a plus 6. So simplifying this one more time, we'll have x squared plus 6x plus 6. Now from here, we want to set each one of our factors to 0. And if we look at we actually have three factors. We have x, e to the x, and this quadratic trinomial. So we're going to set x to 0. We're going to set e to the x to 0, and we're going to set our quadratic trinomial to 0. This is, boom, the answer. In the second one, e to the x equals 0 has no solutions. If you recall, anytime we have an exponential function, meaning a base that is a positive non-1 number, like e is 2.7, ... This can never be 0. No matter what x value we plug in here, we'll always get a positive number out, and therefore we'll never get 0 out. So this does not provide us any solutions. It's not solvable for, like, there's no x value that works. Then in our final factor, we want to see if it's factorable. It's not. There's not two numbers that multiply to 6 that add to 6. Therefore, we can use the quadratic formula to solve this. So we'll have the opposite of b, plus or minus b squared minus 4 times a, which is 1, times c, all over 2 times a is 1. So solving this, we'll have negative 6 plus or minus 36 minus 24. 36 minus 24 is 12, all over 2. When we simplify the square root of 12, we'll get root 4 root 3, so we'll get 2 root 3. And then we want to triangle simplify the 6, the 2, and the 2, the negative 6 rather. We can divide them all by 2, so we'll have negative 3, 1, and 1. So that gives us negative 3 plus or minus root 3. Now these three numbers here are all of our potential points of inflection: 0, negative 3 plus root 3, and negative 3 minus root 3. They are like our test values to test for concavity on either side of them in those intervals that we'll create. But we don't know if they're points of inflection until we actually see if the concavity changes. So at this point, they're just the potential points of inflection. So what we will do is set up a sign chart for f double prime. And my calculator tells me that -3 minus root 3 is about -4.7. So it's the most, left value. Then -3 plus root 3 is only -1.26, so that goes second. And then this is 0. All right, so again, this is approximately -4.7. And this is approximately -1.3. Just so we know where we're at on the number line, you do not have to do that, just so you know like approximately what they are. Okay, so now we want to plug in some values for f double prime. We know that these three pop out 0. And I brought over our factored f double prime so we could remember what it was. So let's plug in a number that's clearly in this interval over here. I'm going to plug in -5. So if we plug in -5 into that interval and test it, we'll have a negative for the x value up front. Remember, e to the x, that's always a positive output. E to the -5 is still a positive number. And then plugging in -5 into this last factor here, we'll have a positive 25 minus 30, so -5. Then plus 6, so just making it a +1. So that's positive. Therefore, a negative times a positive is a negative. The next number I'm choosing to plug in is -2, just because I know it's in between these two values. So when we plug in -2, we'll have a -2 out front for x. E to the -2, e to the anything's positive. Then plugging into this last factor here, we'll have 4 minus 12 plus 6. So that's a negative number. A negative times a negative is a positive. Because this value right here is -1.3 something, it was like -1.26, I know that -1 lies like right here. So I'm going to plug in -1, so I don't need to plug in any like fractions or anything like that. Just try to keep this as simple as you can. So we have a -1 out front. E to the -1 is still positive, right? It's just 1 over e, so that's a positive number. Then if we plug in -1 here, we'll have 1 minus 6 plus 6. So those cancel, so we'll have 1. So that's a positive. Therefore, we'll have a negative output. And lastly, the last one should be easier because we can just plug in any positive number, anything to the right of 0. So I will plug in 100 just to have fun with it. So if we plug in 100, we'll have a positive, and then e to the 100's positive. And then in this last one, we'll have, wow, 100 squared, that's huge, right? Then we'll have plus another 600 plus 6 more. So that's positive. So right here in this interval, we are positive. We can come to the following conclusions about our intervals of concavity. And then, because points of inflection are where concavity changes, we know that we have points of inflection at the points when x equals -3 minus root 3. We have them at -3 plus root 3, and we have them when x equals 0. Now, I'm not writing the whole coordinate point there. I just made this function up, and it ended up being pretty nuts, so I don't really want to plug this in to a function. So we can just say we have points of inflection at when x is these three values because our concavity changes signs there. And just for like a cool look at all this work we just did. It looks really cool from far away. In this video, we talked about concavity and points of inflection and basically how we can use the second derivative to find both of those things.